Let's talk about RLC circuits. Let's see if I can get this thing to move. Maybe. Okay, we're going to discuss series circuits that contain resistance, inductance, and capacitance. We're going to discuss the impedance of an RLC series circuit. We're going to review RLC circuit values and discuss series resonance circuits. What is resonant? What's resonant? It has a 100% power factor. It has a 0-degree phase angle. That's a resonant circuit. Okay? In a series circuit, there are only one pathway for current. Okay, therefore the total current is flowing through each component. However, the individual component voltages will have varying phase relationships. Each component will also have an ohm value found by dividing the component voltage drop by the circuit current. The component power values resolve with vector addition. In other words, don't say vector addition, say triangles. Much easier to think about. Okay. And here in the resistor, the voltage and the current are in phase. In the inductor, what is leading? Eli the Iceman. Eli is inductive, L for inductive, right? E before I. Okay, voltage before current. So we know what is leading, right? Okay. And so then the last one is our capacitive circuit. So that's the ICE circuit. So current before. Very good. All right. Okay. So we're going to look at this RLC series circuit. And we already know that Z stands for impedance. IT is total current. E sub R is the voltage drop across the resistor. P is true power. It's measured in watts. L is the inductance of the inductor. E sub L is the voltage drop across the inductor. VARs, that's reactive power. Capacitance of the capacitor in farads. Voltage drop across the capacitor is E sub C. VARs, S sub C. Or VAR sub C, reactive power of the capacitor. And volt amps, that's apparent power, power factor, and the phase angle are related directly. Now, I want you to ignore this slide. We're not going to do this ever again this way, okay? Say yay. All right. This is how we're going to look at these things. We're going to look at them as, if this is going up, what's going on? Here we have an X sub L, which should be on this far side in my opinion, but that's a whole different opera. We have a resistance, which is never going to change, right? We can't change the resistance of a circuit, generally speaking. But we can add some X sub C. Now imagine if both these lines are out here. Let me start drawing on this thing and we'll screw things up really good. So our X sub L is going up. Everybody agree with that? In our previous drawings? Okay, now look at our X sub C. Now in this one, we've just got this little bit right here, right? So let's take this amount. We're going to go right about here and we're going to go back down. So a resultant is a new triangle. What a concept. Easier to work with. We're going to look at that in just a minute. Okay, let's look at our RL only at first. So we see we have our resistance and we have our X sub L. And let's say that our X sub L is coming all the way up here to 24. And let's say that our X sub C down here, now you remember that X sub L and X sub C are 180 degrees out of phase, right? They're exact opposite in phase. What's 24 minus 8? 16. We still have X sub L, right? Because our X sub C is smaller. Everybody agree with that? So now we have a new triangle. What happened to our phase angle? Phase angle went down, our efficiency went up. We're approaching, we're heading towards unity, right? We're going towards that. Okay. Yes, we knew that. I is E divided by Z. Amazing, I tell you. And resistive voltage drop, we know what that is. All right. True power can be computed using the pure resistance values. Actually, let's go back over that. Let me say that again. True power can be computed using any of the pure resistive values. In other words, if you knew the total power as a result of the voltage drop across the resistor and the current through the resistor, you know the true power that this thing's making, right? Because everything else in this thing is VARs, right? Okay, so this is, well, when we get to the VARs and the power, we'll talk about that later. Okay, we all know all this good stuff that X sub L is 2 pi FL and X sub C is 1 over 2 pi FC, right? So one is almost the reciprocal of the other, right? Multiply them together, you get a 1, right? What's that 1 called? That's called unity. Ah, when they're equal, that is. Okay. Okay. I don't want to say much about that. I think we're blowing a bunch of time away here. Apparent power, we know what that is. Forget about this lower part. We're not even going to look at this anymore. We don't do it like that. This is how we're going to do it. We're first going to calculate our RL, our inductance and our resistance. And then we're going to reduce that with our X sub C, with our capacitance. Equal theta, the cosine. Here we have an example circuit. We have an ammeter. Oh, isn't that fun? Let's see. Okay. Series resistance. When an inductor and capacitor are connected in series, there will be one frequency at which the inductive reactance and capacitor reactance will become equal. This is the resonant frequency. The current will only be limited by the pure resistance. Now, we're going to work in just one frequency, generally speaking, either 60 cycles a second, or we might, as in exercises, we might use a 50 cycles, which is the European version, or 400 cycles, which is aviation stuff. But mostly we're going to work in 60 cycles. Okay. And a lot of this, when they're talking about different frequencies, they're talking radio stuff, okay? Which isn't our direct concern. Okay, but where it does come into play for us is when we're trying to do power factor correction on a motor, which is what we're going to get to in just a minute. Let's go down here, and we have a review of what we've just learned. Isn't that wonderful? We've learned so much. Isn't this great? And the part I've been looking for is right here. Okay, now, let me hit pause for a second because I want to grab a couple numbers. All right, so we're going to assume we know a few things about this motor. And we're going to assume that we have taken a resistance reading across the total windings, okay? And we have 8 ohms of total resistance. And we know that we have a full load amperage of 9.8 amps. Okay, so that tells us our impedance, doesn't it? So let's plug that in. We have 120 volts, and we're going to divide that by 9.8 amps. That will give us the total impedance, right? 12.24 something something. So we have 8 ohms as our true DC resistance, right? But we have a triangle, and we know that we have 12.2448 ohms is our impedance. So let's find how many ohms of inductive reactance we have, okay? So what side of the triangle is this over here? That's the opposite, right? So let's say sine, cosine, and what am I leaving out? Tangent. And that's oh hell, another hour of agony. Okay. Okay. And we want to find something where we have the angle. So first we want to know the angle, right? So what function do we have right now? We have the hypotenuse and we have the side adjacent. So we have the cosine, right? Okay. So let's find the cosine and find the angle by saying second function cosine 8 divided by 12.2448. And we're going to find that we have a, that can't be right, 0.24 angle? No. Second function cosine 8 divided by 12.2448. Oh, I must not have put the decimal in the right place. 49, 2062, and so on, degrees. And we want to find this. So now we have the cosine, so we have the angle, so we can have the cosine of the tangent. And if we're looking for the opposite, we can start plugging things in and say the sine of this angle is equal to the opposite divided by 12.2448. Everybody see that? And we already know that the sine of this thing, or we don't know it already, but we can find that by, we've got the angle in our calculator right now, so we're just going to put in sine, second function, answer, enter. And the sine of this thing is 0.75. And that's equal to the side opposite divided by 12.2448. So we multiply both sides by 12.2448. Then 12 point, etc. is over here, and it'll drop out. Oops. So we've got 0.75 and all that long number in here. We're going to hit multiply, and then 12.2448. Then we're going to get 9. Now what is that? Okay. Now, let's talk about what we want to do with this information. We've found the RL circuit, right? But what we're talking about is RLC circuits, but I want to tell you why we want to talk about them. Why we want to talk about this is we want to power factor correct this motor down to somewhere near 0 degrees. Not necessarily 0, but we want to get close. And we don't want to overshoot. So what we're generally going to do with real world motors is we want to add capacitors to this motor. okay? And we want to get rid of most of this, right? We don't want to overshoot, so we're going to say, well, we only want, now we're going to have to round up or round down. This is why we shoot for 95% of this. We're going to shoot for 95% of this because when we find a capacitor, it won't be exactly what we want. We've got to go one way or the other, right? So now we're going to start experimenting. Now remember, can I save that? I wonder. Now we want to get rid of most of this, right? So we have 9.27, and let's say I want to multiply that times 0.95. So what I'm going to shoot for is I'm going to shoot for 8.8 ohms of X sub C. Now what do we know about the formula for X sub C? X sub C is equal to 1 over 2 pi F times C. And if we're looking for the capacitor that will do the job that we're looking for, this is the formula we want because we have our ohms, 8.8 ohms. That's our X sub C. And we have the formula 1 over 2 pi FC, 2 pi FC. And we want to take this out because we know that's really 1 over 377 times C. Everybody agree with that? So what if we wanted to get the C all by itself? Or at least get the C on one side and most of the numbers on the other side. We could multiply times 377. Okay, let's do that. Is that correct? Is that what happened? If we multiply both sides by C, by 377, we get left with 1 over C? Okay. So what are we going to do with that information? Well, I've got my 8.8 in my calculator, and now I'm going to multiply times 377. Now I have a big old number. That's not helping me at all. Oh, that's right. I want the reciprocal of that number. X minus 1, enter, 0.000301. What does that mean? 301, the first 3 would be milli, right? So the next 3 are micro, right? So 301 micro, is that right? Yeah. You know what? They don't make a 301 microfarad. Could I round this to 300 and plug it back in and go the other way and find out what resistance I wind up with? Yes! Brilliant, I tell you. Great idea. Let's do that. So let's round this, and we're going to say that we're going to use a 300 ohm X sub C. So now we're going to get rid of this stuff up here. We're going to change the formula because we know that X sub C is equal to whoops. Oh, wrong. No wonder I put it in the wrong place. 1 over 377 times C. What is our C? Okay. So what you're saying is, let's ignore the 1 over first. Okay. Let's just deal with our point. Now I'm going to take this out. I'm going to put in 0.0003, right? Times 377. Probably going to get a pretty small number, like 0.1131. But what is that? That's the reciprocal of our X sub C, right? Somebody say yes. Let's take the reciprocal of this then, and we wind up with 8.84. 8.84. Is that too much or too little? How much did we want? We want 8.8. That's too much. We will shoot past this point right here. Because we want to get rid of how much? Oh, so we could do that. We have up to 9.27 to get rid of. So we can go with a 300 microfarad capacitor, right? At the right voltage. Okay. And that will give us 8.84. So let's look at that now. Okay, this is our X sub L, right? 9.27. And now we're going to come down with our X sub C of 8.8417, whatever. And we're going to put in 9.27 minus second function answer, and it's going to tell us we're going to have something left over right here. We're going to have 0.428 ohms is our new X sub L. We've got a little tiny X sub L left, right? We have a new triangle. We have a new phase angle. What was our phase angle before? 49 degrees. Okay. So if we connect this capacitor, we're going to get down to a very small phase angle. Is our resistance any different? No. Can we find what function do we have here? If we have the X sub L and we have the resistance, we have the tangent, don't we? Let's go second function tangent. Okay. And it's, wait a minute, that number we just had, second function number, second function answer, divided by 8. I'm going to close parentheses just for the S's and G's and hit enter. And it says 3.06 degrees. Now that's not 0 degrees, but it's darn close. I can live with that. We have a new phase angle. We went down from 49 degrees down to 3.064 degrees. Okay, what's the power factor of that? Very nearly 100%. So let's say cosine, second function answer, what's the cosine of 3 degrees? 0.998. It's 99.8% efficient. This motor just went up from being about, what's the cosine of 49 degrees? Somebody look that up. What's the cosine of 49 degrees? Cosine of 49.206. 65, we took a motor that was taking in power. It was making, now let's go to the power triangle. What a messed up slide, but I'm afraid to move it because I'll lose everything. Okay, let's multiply up, wait a minute. Cosine of 3. Okay, so we have a cosine of this angle is 99.99857, so it's 99.857 efficient. So let's multiply. I'm going to break down and hit clear. I'm not sure why. But I'm going to multiply 120 times 9.8. So the apparent power that I'm taking in is 1176 VAs. What was our power factor with, what was our cosine of 49 degrees? Okay, times 0.65. So before we power factor corrected this thing, we would have turned this into, I don't have room for a new triangle, and I'm afraid to move this one. I can't move it. I know what I'm going to do. No! That's not what I wanted to do. No! All right. Okay, we've got to put a new triangle up anyway. So, what was our impedance? Okay, so what we know is that our previous triangle, before we power factor corrected this motor, it was taking 1,176 VAs, which is what you're paying Edison for, right? And it was cranking out 764 watts of cranking force. Everybody on that? Okay, now, when we power factor corrected by adding a capacitor, we wound up with 3.06 degrees. Is that correct? Okay, so if that's true, then we're going to have a power factor of, what was it, 99.8? So let's say that our power factor was 99.8 what? 85. Okay, times 0.9985. So what that means is that this same exact motor is now cranking out 1,174 watts of cranking force. Now that's not what's going to happen, because we don't need 1,174 watts of cranking force. What's going to happen is this motor is going to run at less than 100% when it's under what used to be full load, right? So if we only need to crank 764 watts with this new power factor corrected motor, what's it going to draw? Now, let me tell you what's going on. What happens here is we're drawing a certain amount of current, right? 9.8 amps. And if we find our new current, it might be more than 9.8. It will almost for sure will be more than 9.8, because now, or will it? But let's say that we only need to make 764 watts of actual power, because we designed this system with this particular motor in mind. But now we have it power factor corrected. Now, when it cranks that amount of power, it's going to draw less current, doing the same work, saving us lots of money. We like that. And when you can offer that to a customer for a very small nominal fee, you can make a happy customer very quickly. Hey, you know, you bought a really inexpensive motor and it's not very efficient. It's going to cost you 10 times what that motor cost you to buy in electricity in the next few years. Let's do something about that. How about we add some capacitors to this and make it a more efficient motor? How about that? You think a customer's not going to want to do that? They're going to want to spend a little more money with you to do a little more work. Always a good idea, right? Okay, so that is why RLCs are important to working electricians, because it's power factor correction on a motor. That's what RLC is all about. Now, why is it that we need to be able to find the size of the capacitor? We have to be able to do the calculation to find the size of the capacitor, right? Okay, that's all you need to be able to do. Piece of cake, right?